Showtime!
Ladies and gentlemen, please make your way to your seats.
Showtime!
Please make your way to your seats. The show is about to begin.
Showtime!
Let the magic begin.
Creating pretty much limitless free energy through this Coulomb Drag.
Coulomb Drag, yeah. Just some things to talk about. We're talking about nanotechnology. So nanoscale devices use Coulomb Drag between flowing salt ions and charges in the device to produce electricity. So we're talking about a nano generator, by the way, that harnesses saltwater gradients for energy. So the way it works is it works by creating a voltage when the electric forces cause charges to flow from one side to the other as ions pass through a narrow channel. That's how things work. Experiments are showing that the effect occurs with both positive and negative ion flows, and with either attractive or repulsive forces between ions and device charges. So there's an amplification effect as the momentum of the heavier ion is transferred to the lighter electrons, which boosts the electrical output. So the design is versatile because it doesn't depend on specific materials or channel shapes. So the key is to ensure a close interaction between the ions and charges. So if you put these arrays, or if you put these nano generators into arrays, you can see the power density of solar cells, which provides a promising new method of generating clean, renewable energy from salt water, such as where rivers meet the sea kind of thing. So in addition to coastal energy production, there are possibilities for applications in fields like biomedical sensors or nanofluidic devices. The thing is it's a simple, adaptable technology, which makes it appealing for scaling up. But obviously, further research is needed to optimize multi-device configurations and things like that. But the bottom line is, this nanotech innovation could unlock an abundant new source of blue energy along coastlines worldwide, which harnesses saltwater gradients, and hopefully maybe surpass solar in some areas. The researchers, what they were doing, the way this happened was they were initially just exploring whether nanoscale semiconductor devices could extract energy from ion flows. So these results pretty much exceeded expectations.
So you mentioned a new word, blue energy. What's the difference between blue energy and green energy?
Water, using water.
How much electricity, how efficient is the energy conversion process? If we set this up at a mouth of a river where fresh water meets salt water, are we getting a trickle we can charge our iPhone, or are we running cities?
Yeah, so based on the fact that the article states that the researchers believe that the arrays could match or exceed power density of solar cells, it suggests that there's reasonably high efficiency. Just to give you an idea, solar panels tend to operate around 15 to 20% efficiency in converting sunlight to usable electricity, which provides a rough benchmark to compare to. But in the article, it didn't really provide any specific numbers for what percentage of the potential energy in the saltwater gradient gets converted to electrical energy. But there's going to be different factors that come into play here, like salt concentration difference, flow rates, precise device geometry. That's all going to affect how much potential energy can be tapped. So again, there's going to be a lot of third-party testing that's going to need to quantify end-to-end efficiency once the prototypes are further along. But in the article itself, it's pretty optimistic about the efficiency prospects. But again, I think it's too early to tell what the exact percentages of potential energy could be. So we'll have to see, though.
A lot of times we go blind into some of these things, not understanding the environmental impacts do we understand, the environmental, what this might do to marine life or coastal ecosystems?
Yeah, so it's a great question. And I tried to figure it out. I tried to read beyond this article, but because it's a newer nanotechnology, it's not fully characterized. There's some initial considerations. The nanoscale size means the devices themselves take up very little physical space in the water. So it minimizes habitat disruption, which is really good. But little is known yet with the effects of the electric fields and ion flows on marine organisms. So they're going to have to do some lab testing there. But the other thing, too, to think about is the materials that they're going to use to manufacture the devices, such as semiconductors, things like that, could leach chemicals into the water. So toxicity studies are going to need it. And then large scale installations obviously are going to affect migratory patterns, habitats, or other ecosystem functions. So any changes into the water, into the ecosystem itself, is going to affect it. If you're integrating it on a larger scale, but if we're talking nanoscale, potentially there's very little, but there's also things like toxicity.
So
there's potential.
Could this technology be used in, say, desalination to also boost freshwater supplies? Does it actually do anything with the salt, the flow, or just?
Absolutely. Yeah, the nanotech that harnesses the saltwater gradients for energy could potentially also be used for desalination to increase freshwater supplies. So here's a few ways that it could work based on what I've read. There's the basic process creates an ion flow through the nanoscale channels. So adjusting the device design and materials could allow selective filtration of salt ions, which would then leave behind fresh water. The other thing is the energy generated from the salt gradient could be used to power an integrated desalination component, like a reverse osmosis membrane. The other thing too is we're still getting into nanoscale devices and things like that. Nanoscale materials and research advances, purpose-built nanopores, again, we're getting into nano again, could potentially sort and separate salt ions from water at very low energy costs. With the devices being deployed along coastlines, it could create drinking water through desalination while also generating power. And then you could also integrate it with existing large-scale desalination plants, which could provide on-site energy production at a lower operating cost. The scalability, efficiency, and potential of harnessing ion flows at the nanoscale could make this a disruptive technology for desalination, because right now, as you know probably, there really isn't an efficient way to desalinate water. Or maybe I'm wrong.
I don't think there's an efficient way, but I haven't actually looked up desalination in a few years. They like we're looking at this stuff. There's easily technologies that can sneak by us that we just haven't seen. But this is great. Like, I love this. How far along are they in the process? They've done this testing. Like, are they, anywhere closer to deploying this anywhere?
Spoiler alert. I didn't say this at the beginning, but the technology is still in the simulation and concept phase. So it's not been physically built and tested yet. So researchers are going to need to fabricate working prototypes and optimize design for efficiency, durability, manufacturability, etc. Proof of concept stage, maybe 2 to 3 years if everything goes well. After initial prototypes, the first real world pilots may happen maybe in the next 5 years. And they're going to be small scale deployments to test performance and environmental impacts in coastal environments. And then assuming that successful pilots with reliable energy generation and minimal ecological risks, commercialization could begin in the next 8 to 10 years. But the nano fabrication techniques required to mass produce the devices at an affordable cost, those are still underdeveloped. So that needs to advance. The manufacturing scale may delay the widespread availability of this. The other thing too is regulatory approval, permitting, policies, infrastructure connections, all that sort of stuff. That's going to really influence the pace. All this stuff is going to influence the pace. But conservative estimates, let's say fully into the market, 10 to 15 years.
Do we see it getting more efficient than the current solar?
I think so. I think even in but again, they're doing simulations, which are like perfect scenarios kind of thing. So maybe they don't, unless there is a breakthrough or advancement in nanotechnology. At the current state of technology, no.
I like what we're doing here, seeing using different things like the ocean, the flows in the ocean, salt in the ocean. What we looked at a few weeks ago, where we were talking about from the vacuum of space, creating energy. This is really cool stuff, and long term, it looks like there's going to be some very interesting energy solutions for us.
Yeah, and way less invasive than those wave generators, or the whatever they're called, the current generators. You know, the things they deploy in the ocean, and when a wave comes, it goes up and down, and then it generates electricity.
Yeah. The more efficient we can get at this stuff, the better. Any final words before we jump to the next one?
I love clean tech like this. I love things, especially if they can adapt it to desalination processes, because that's a huge problem, especially in third world countries, and getting access to fresh water and things like that. So yeah, and going forward.